Hi, this is the Sedra Smith Chapter 5 Small Signals Analysis of a MOSFET. What I'm going to show is some of the techniques, how to do the small signal analysis. Uh, and one of the things that I want to start first is how to derive the input impedance, because later on, knowing what the input impedance of the terminals can simplify your, let's say, deriving gains. So it's a good way to start on developing some of the techniques. Anyway, here's a, let's say for example, if you take the output at the drain, say this is out, and this is your input signal, that would be your gate, and that would be your source. Okay, so if your signal comes in on the gate and it comes out on your drain, then this topology would be a common source. Okay, and you can have a circuit that is being powered by a current source. Typically, this will be another MOSFET. Okay, and which is operating as a current gain or a current source. Or you can also have it act not only as a current source, you can have an amplifier sort. Okay. And many times you need to know what the input impedance would be looking into the source. Okay, so to derive this, you have to make a substitution. Okay, and we're going to use the small signal model. I'll call it SSM, and basically you're going to have a junction, which will be the gate. This would be positive, that would be negative, and then you have a current source. This would be your drain, and then this would be your source. And this current source is actually defined by GM, which is the transconductance of the MOSFET, times VGS. So basically, this current source is dependent on whatever your voltage across VGS. So this is the absolutely simplest MOSFET model, and you can plug this model into this circuit to derive the input impedance. So let's go ahead and do that. Now when you do a AC model or a small signal model, your input source is shorted. Okay. Your output source, or actually your VDD, acts as a ground, or is an AC ground. Okay. So now we have that. So now we are ready to plug in the model. So you have ground, and you're going to have RG. Okay. And then this is where we plug in this model. And I'll put a little dot like this. Put the negative here. Okay. Now If you notice here, RD is ground, so you would put RD here to ground. Okay. And then this would be your source, this would be your gate, that would be your drain. Discard this RD. Okay. Now what we're gonna want to do is we want to know what Zn is. So the way we do it is we add a VT, or a voltage test. That voltage test should generate an IT current. Okay. So now we're set up. Okay. So let me add another page. Okay. So the first thing you want to do is you want to define VGS. And when I say VGS, I want to define this voltage. Okay. And I think this is a powerful technique taught by my professor, Ken Noren. When you say VGS, in reality what you're saying is voltage from the gate minus voltage of the source. Okay. And what's neat about this technique is then it makes it more intuitive. So in this case you want to know what VG is. I'll go ahead and do it here. And VG is this: VG, VS, VD. Okay. So if you look in here, this is the positive, this is the gate, and if you notice, there's no current flowing through here, and if you have no current, there's no voltage drop across the resistor. So if there's no voltage drop, since this is connected to 0 volts, that means that this is also 0 volts. Okay, so this tells me that this is 0. Okay, so now we look at this term, Vs. So in this case we look at that node. Okay, and if you notice, this Vs is connected to Vt. So actually Vs, the voltage at the source, is actually Vt. Okay, so then this VGS is equal to minus Vt. Let me see if it's correct. Yeah, it's correct. Should be correct. Okay. So now we can do a Kirchhoff's current law at Vs node. Okay. So we have this Vt that's going into this node, but then you have this current, and this current is dependent on Gm VGS. Okay, so basically you have two currents that are entering the Vs. So when they enter, it's actually negative It minus Gm VGS equals 0. Okay, so now we can plug this into here, and we'll continue to hit here. It minus Gm minus Vt equals 0. Okay, now since this is a negative, that's a positive, so this becomes GM VT equals, bring that to the other side, IT. So now when we do a okay, well this is actually the Zn, is the impedance. That's the impedance looking into the source. So basically, if you go in here, anytime you look into the source, you should automatically think that it's 1 over GM. And that's it. Okay. So let's try a different topology. Okay. Let's say we want to look at the impedance. Looking into the drain. Okay. So assume using the same schematic, we're going to look in here. Zn is the drain. Okay. So basically we use the same technique. You would have your RG. This would be your VGS plus, negative. And let's assume that this is grounded, your source. So this is VS, VG, and this is VD, and this is RD. Okay, so we want to know what's Zn, okay, or in this case it's an output Z out. So same thing, we add a voltage source. It's a VT, or it's a test, and now we have IT. It's a current that is developed. Again, try to define VGS, and again I like to break it up into this. VG, no current, so basically it's going to be 0 volts. And then if we look in here, VS, and notice it's connected to ground. So that's 0. So then VGS equals 0 volts. Okay. So that's already defined. Okay. So now we have it. Now we want to do a KCL at the drain. Okay. So this is GM VGS, and since it flows in this direction, it would flow like that. Okay. So, and you had current coming in. So if current comes in, it's negative IT, and then since this is leaving, it's a plus GM VGS equals 0. Okay. So, let's see. Oh, hang on. And I forgot one little. Okay. So you have that current, and then you have this current here. Okay. Now, because VGS is 0, all this term goes to 0. So that means that this current does not exist. And if it doesn't exist and this current is coming in, well, where does it go? It can't come in here because it's 0. And a current source is an open, it's a high impedance. So instead of flowing through here, it flows through the resistor. Okay. So then that resistor, since it's flowing out, it's negative IT RD equals 0. Okay. T plus, okay, made a little mistake here. Okay, so current and this, the resistance that is actually a VT. And since we want a current should be that this IT is actually IT RD. So IT is actually VT RD. So substitute that in here. IT plus VT RD equals 0. Flip this to the other side. So now we end up with T equals RD. So that's the output impedance. So basically, since this is an open, the only thing that you're reading is this RD resistor. Now, if you have a load, you can put that load in series, or no, in parallel, and then you would have VT IT would be RD in parallel with RL. That would be valid if you include RL. Now the last one is the impedance. Looking into the gate. Okay, and this is really super simple. For the VT, IT's VGS plus negative this would be GM VGS Now, if you put a voltage source here, since there's an open, there's no current flow through here, no current. Okay, so that assumes since you have no current, you basically have a VT over IT, and as let me put it this way, as IT approaches 0, the whole VT IT term actually goes to infinity, which means it's an open. And it's open because there's a parallel plate. In other words, there's a parallel or capacitance between your gate and your source. So in a nutshell, we're able to figure out all the impedance of the three terminals, looking into the gate, source, and the drain. In the next video, I'll show how we can use at least one of the impedances to simplify voltage calculations or derivations. Thank you for watching.